Welcome everybody, this is David Pike, otherwise known as the Connector Geek, and I'd like to welcome you to the latest in our series of Ask the Expert videos. Today I'm joined by Brian Engel from Amphenol.
Good morning.
Great to see you, thanks for joining us. So we're going to talk about Amphenol, and Amphenol is familiar to almost everybody as one of the giants of the connector industry, but just to make a change, we're not actually going to talk about connectors today. Amphenol is a big player in the world of sensors, and in particular, sensors that are used in the protection and management of battery systems. Now, here on Design Spark recently, we've been talking a lot about sustainability, and alternative energy sources and the storage of the energy they produce is obviously a key topic in that sustainability topic. So we've been talking about batteries, we've been talking about storage systems. That's why Brian's joined me today. And so before we start, I'd like to ask Brian just to give us a teeny bit of background about his knowledge and his area of speciality. So Brian, over to you for a second.
Sure. So I'm Brian Engel. I'm a Director of Business Development for the Amphenol Advanced Sensors Technology Group. And within that role, I'm responsible for developing new technologies to support new client challenges, new industries, and emerging technologies. Specific focus right now is on electrification, battery, motor, inverter technologies for EVs, batteries for stationary storage, as well as for marine, submarine, and aerospace environments. In addition to my role as the Director of Business Development for Amphenol, I have a few other roles that I play in the industry as well. With the Society of Automotive Engineers, I am currently the Vice Chair of the Battery Standards Steering Committee for SAE. Now, under that particular role, we have approximately 23 different working groups responsible for over 50 different standards associated with battery technology, battery safety as it applies to the transportation environment. And I also have a responsibility toward an organization called NatBat, which is a global organization of battery manufacturers, the supply chain, and the end users of these various battery technologies that we're deploying globally. And that market is now approaching the $1 to $1.5 trillion point in a very short order as the entire world makes the transition from heat combustion technology to electricity and battery power.
Fantastic, Brian. Thank you for that. And hopefully to all the viewers, it will give them an idea of your expertise and your breadth of knowledge in this. And we're not just talking about Amphenol solutions, we're talking about the battery industry as a whole. So you touched upon a large part of what you do is in the transportation industry. And I think for many people with the growth of electric vehicles, transportation, when we talk about batteries, that's one of the first things that comes to mind. So when we talk about that specifically at the moment, we're talking about the lithium-ion batteries, are we not? Can you just give us a tiny bit about the technology behind that?
Sure. So lithium-ion batteries have been in the consumer market for a few decades now. They started in the early 90s, and they've moved from the consumer products in small scale to much larger scale. There are now products in the field that are as large as large marine vessels, ferries. We have lithium-ion batteries going into electrified aircraft. We have lithium-ion battery systems in automobiles and transportation. And obviously, people know the likes of some of the projects from Tesla, GM, VW, and many of the other manufacturers as they make this pivot. But they're also in heavy-duty commercial vehicles as well. We're seeing excavators and bulldozers and many other pieces of mining equipment that are converting to this technology. And, generally, we're seeing a huge growth in this industry and literally following Moore's law of improvements in the technology in terms of the scale, the energy density, the power density of these devices.
And is it fair to say that this technology does dominate the market at the moment? Is this the way that everybody is going?
Yes. In order to meet climate objectives, many countries have signed on to elimination of internal combustion engines throughout their fleets, whether they be in passenger cars, heavy vehicles, or even stationary applications. So this is definitely not a fad. It is a technology shift that is very much akin to that of 100 years ago when we adopted internal combustion engines to replace horse-drawn technology and steam technology.
And that then leads us on. We've touched upon the idea of the number of different applications that these batteries are going into. I think the key thing here is we talked about energy density. So when we're talking about energy density, what does that mean? What do people need to understand when we're comparing, for example, combustion engine powered gasoline, petrol, and batteries? What is energy density and why is it important?
Sure. So energy density has to do with the either the amount of energy that you can store per unit of volume or per unit of weight. Generally, while you compare on a pure level, say hydrocarbon-based fuels, diesel, petrol, to battery technology, they appear to have much higher energy density. But the conversion in the application is really where all of this inefficiency occurs in the internal combustion engine. So not only do you have these the emission of these harmful gases, the CO2 that contributes to climate change, as well as VOCs and CO and NOx that are also emitted from these internal combustion engines. Generally, your efficiency in converting that chemical energy from combustion to power to the wheels and electrical energy on the vehicle is you lose about 70 to 80% of that raw energy that's stored, where you have a much higher energy conversion rate from battery technology to basically tractive effort to the wheels and electric energy utilized by the vehicle. So what we find is that electric vehicles in general are, while they're improving in range, they're already superior to combustion engine vehicles in performance as far as torque off the line. You'll see if you look at a variety of different records across a number of different tracks, EVs dominate Nuremberg, Pikes Peak, and many other of the competitive, let's say, benchmarks for vehicle performance.
And so I think it's probably important to talk a little bit about the scale of what these batteries are doing, because the original lithium-ion batteries, or things that people might have been used to 10 years ago, these were batteries that were powering your mobile phone or your smartphone. So we're talking a few volts, maybe a few amps. When we're talking about these big, heavy industrial applications, whether it's commercial vehicles, whether it's the domestic car that's sitting on your drive, or even these marine applications, we must be talking about hundreds of amps, even thousands of amps, hundreds or thousands of volts. So these are large amounts of energy, aren't they?
Yes. Not quite hundreds of thousands, but certainly a little bit higher than your cell phone. So to kind of give you a sense of perspective, the voltage levels of many of these battery packs in a transportation application, in a typical electric vehicle, you can have anywhere from, say, 65 kilowatt hours of energy storage all the way up to maybe 100 and 135 in a pass car, high performance pass car. And then you get into the heavy vehicles, you're now talking about 200 to 400 kilowatt hours of capacity and even more. And generally, the voltage levels for these devices much higher than what you'd expect to see in a consumer product. So you're looking at systems that are going to be in the 300 to even 800 volts, and we're even seeing in development, kilovolt level design of these systems. And the higher the voltage, basically, the smaller the conductors, and that saves weight, which is great. But then you also have to be very careful of the design of those systems. Generally, with that added energy density, power density, comes the higher voltages and higher currents. We're even seeing now, especially with the fast charging applications, megawatt level charging capability, which is, a little bit of a challenge to manage, but the industry is doing quite well in terms of being able to provide a product that may have taken 8 to 10 hours to charge as little as 5 years ago, and being able to charge it in 15 to 20 minutes, which is about the amount of time you'd typically spend at a gas station refueling a vehicle.
So we've been discussing the batteries that are being used in some of these heavy applications and the amount of energy that's being pumped into them and being stored and then obviously being used. So I guess that leads on to a question which basically is, are lithium-ion batteries safe?
Yes, they are very safe. Now, we've had a lot of early experiences with consumer products. People may remember the Samsung Galaxy, some laptops, other products like that. 10 years ago, the quality of the product, our understanding of the requirements for design, and the ppm, or the basically the faults per unit of surface area of the separator and the active surface area of the cells. It's improved dramatically in the past decade. Current EVs basically are about 90% less likely to have a failure mode resulting in a fire than a typical internal combustion engine. And just to cite a few facts from NFPA, there are about one fire event in combustion vehicles about every 3 minutes in the United States that first responders have to deal with. However, they don't make headlines, and generally they don't make headlines because it only takes a first responder about 10 minutes to put that event out once they're on scene. We've got 100 years of experience and tools to deal with those situations, so they're really non-events for the press. So you typically don't have those things making headlines. Now, lithium-ion batteries, it's a new technology. It's very interesting to people. So what we find is that it tends to attract attention to begin with. And then there are some unfortunate outcomes that, even though the probability is far less, generally when a battery, a lithium-ion battery, catches fire from various sources, maybe a high-speed collision, as in many cases is what we've seen in the field today, and many cases well beyond the crash standards that are part of our vehicle design today. You know, our vehicles are designed to crash at 35 miles an hour safely, and some of these vehicles often crash at 80, 90 miles an hour and faster. But to kind of get to the point, it takes first responders much longer to deal with these events. It's a new technology. Our techniques and tools for dealing with it are new and in many cases inadequate. And training is still inadequate. So generally the challenges here are first responders will spend hours on the scene. Batteries, because they carry their own oxygen, they can continue to support combustion, decomposition for quite a period of time. They can also have reignition events. So unlike an internal combustion engine vehicle fire that you put it out and it's done, these can reignite if you don't remove the stranded energy from the battery pack. So there are a number of challenges that first responders have to deal with when these events occur. So even though they are far less likely to occur, and I certainly would feel very safe parking EVs in my garage, I would say that when an event does occur, because it takes so much time, so many resources to deal with, they tend to make headlines. So we tend to see them in the press, and we tend to kind of overemphasize that safety concern. However, the one thing that should be recognized with the hazard is when a lithium-ion battery does start to vent, it does release both flammable and hazardous gases. They have volatile organic chemicals in the electrolyte. They can release hydrogen fluoride gas. They can release hydrogen gas, substantial amounts of carbon dioxide as well. And all of those things can contribute to a number of hazards: the flammability hazard, the asphyxiation hazard, exposure hazards to certain chemicals. So certainly if you are exposed to one of these events, you do want to stay clear of the plume and let trained first responders deal with the incident.
But I think it's also interesting I think it's important that we bring up something that we talked about when we were preparing for this interview. You talked about the challenges that people faced 100 years ago when gasoline was new, when people were using petrol but not used to it. And it's easy for us to forget that there were huge problems 100 years ago when gasoline became new.
Yes. I could say that 100 years ago, a lot of carriage barns burned down. And it was because the fuels we used at the time, kerosene, was a very dense hydrocarbon. Typically, you could carry kerosene in a pail. It wasn't a problem. You carry gasoline in a pail. You put it on the floor of a carriage barn 100 years ago, and those vapors, that plume, basically, as that gasoline got hot, would settle all around the pail and along the floor of the carriage barn. And if you happen to have an ignition source anywhere near it, the gas plume could actually ignite. And so we had a 100-year learning curve on that technology, and we take that for granted. And we're on a very steep learning curve with this technology. So we need to accept the fact that there are going to be issues in the short term. We're doing our very best to deal with them. And from a standpoint of safety, it's already safer than the current technology, and we're going to improve upon that.
That then brings us on to one of the things we want to talk about today is sensors. You represent the sensors division of Amphenol, and from what you're understanding and from your expertise, you know how sensors can be used in the promotion of battery safety. So let's touch upon that at the moment. Let's talk about a few of the things that sensors are doing to keep these batteries safe. What roles do they play?
Okay, so generally, battery systems, they like the same temperature that we do. They don't like to be colder than -10, and they certainly don't like to be any hotter than about 50 C. Now, to do that, you have to maintain that battery temperature through a sophisticated control system. You need heat exchangers to both heat and cool the battery, and that requires some intelligent control as well as feedback, because you want to do it in an energy efficient fashion. So we typically provide into the industry temperature sensors for monitoring cell temperature, for monitoring bus bar temperature, and then monitoring the heat flux through the heat exchanger system. So monitoring the coolant temperature as it goes through the heat exchangers, refrigerant if it's being used in the application, and then providing that as feedback to the control system, so that the control system can flow the optimum amount of coolant, make sure it's rejecting the appropriate amount of heat, and anticipate the needs of that battery pack. A battery pack is a fairly large device with a fairly large thermal mass. So generally you want to understand your loading so that you don't get behind an overheat condition or an overcool condition. And some of the things that are challenging for batteries to deal with, they don't like to charge when it's very, very cold, very much like us. So they tend to need to be warmed up beyond that -10 C. Under that -10 C temperature, if you're trying to aggressively charge a cell, you can actually form lithium dendrites. Those lithium dendrites are like a hardened crystal inside the cell that will eventually penetrate the separator and cause damage to the cell. So that's why generally we want to keep it above the -10 C. And then below that 50 C point, generally above that 50 C point, the challenge that you have with the temperature is you end up getting reactions inside the cell as you're charging or discharging itself that you don't want to have. And those include gas generation that can cause physical damage inside the cell.
It's interesting that we talk about the physical changes to the cell. One of the things that we talked about during our preparation for today's interview is that you explained that the physical changes within the cell that might occur if a battery, for example, was discharged too far, and you just talked about how temperature can affect the physical makeup of the cell itself. And I'm guessing that's one of the things that's going to cause the damage and cause the danger that we talked about earlier.
Yes, so there are three types of stresses that a battery can undergo that all generate physical stresses in the cell. So the first is basically packaging stress. As they're installed in the pack or the array, they're generally compressed to limit their expansion. We have three different types of cells that are generally used. We have cylindrical, which look a lot like the consumer product you have now. You have prismatic, which are basically a big metal can. Think about, like, say, a 9-volt battery, but maybe wider and much, much bigger. And then you have pouch cells. All of those cells, you have the physical constraints around restraining them as part of an array. Then you have thermal stresses on the cell. So as the cell gets hot, the materials inside want to sell. And then you have something called intercalation stresses. Now that is basically the presence or absence of electrons. So as you stuff more electrons into the cell, it also wants to swell up. So as you combine all those different stresses, you get a lot of material movement that is attempting to happen inside the cell. And you want to have very, very tight control of that, because the more that material moves around over time, more it's going to degrade the performance of the cell. And generally, that swelling can be a few percent. So if you can imagine, these devices are basically, we refer to them as a jelly roll. So you've got the active materials, and you've got the separator materials, and then you've got current collectors, a lot of other components, but they're basically rolled up like a jelly roll and then stuffed inside the package. And then that jelly roll is trying to swell and is trying to shrink. And as all of that is going on, you've got a variety of different chemical reactions, electrochemical reactions, generating heat inside the cell that you have to deal with. And then if you do start to have aggressive use of the cell, you'll actually generate gases. And so an overly aggressive charging, if you're charging too fast, charging above the limits of the cell, in other words, trying to stuff too many electrons in the cell, then you can actually get decomposition and gas generation inside the cell. And those gas bubbles can cause problems, just like they do for us. They have the ability to move around inside the cell, so they can cause physical separation of the materials. They can chemically interact because in many cases those decomposition gases can be hydrogen, carbon dioxide, and water vapor. And of course, if we all remember our junior high science class when we took the battery and we put the two leads in the water and we got oxygen on one lead and hydrogen on the other lead, the same thing can happen inside the cell. If you start to decompose components in the cell, you do get a water vapor inside the cell, and it can actually hydrolyze. And if it hydrolyzes, then hydrogen is a byproduct, and the oxygen contributes to other decomposition reactions in the cell. So all of this has to be managed very carefully across an array that may be anywhere from a few hundred prismatic cells to a few thousand small cylindrical cells in a typical traction battery system.
That's fascinating, especially for someone like me whose only real experience with batteries has been, as you say, those domestic types. And the natural reaction is that the physical size of the cell is fixed, and it's effectively a monolith. It's a solid block. The fact that there are physical changes going on within the cell, and then, as you say, you multiply that by several thousand times potentially, each one of those cells may be acting slightly differently. Then I think it's interesting for us to realize that there's stuff going on inside these cells that we're not necessarily aware of. And so what are some of the roles that sensors are playing in protecting us against these things? We talked about temperature, and I'm guessing temperature sensors are one of them, but what other types of sensor are common in this application?
Sure. So you have voltage and current, and you're going to measure that at a number of points in the system. Because in many cases, you're going to measure up to 800 volts out of the pack or into the pack, and then you're going to monitor current at the module and pack level as well. So you've got voltage, current, temperature. Those are the three primary measurements that are performed at both the subsystem and at the full system pack level. But you also have things like as you have this system engaged in other devices, you may be monitoring the performance of those other devices. And I'll give you an example of an application space where you have a temperature measurement, but it's a little bit unique. Because some of these systems operate at such high voltages, they'll have inverters and converters to shift that voltage up or down. So, for example, you may have an 800 volt system, but you may have to knock that voltage down to, say, 400 volts or even 48 volts or 12 volts. And so you'll have inverters either on board or off board. Many of those inverters and converter devices, we think of them as transformers, very much like the devices that that come with your laptop. Those are transformers too, but these are a much larger scale with much higher current loadings, and they're designed differently. Now, they can generate a lot of heat, and because the voltages are very high, you may not necessarily want to make direct contact with those current-carrying devices. There are some standards around spacing high voltage, high current conductors to make sure that you don't get dielectric breakdown. In other words, the insulation between two conductors, if there's a big voltage potential across them, you can actually break down that insulation material over time and cause a short, which you don't want to do. So to monitor temperature of certain connection systems and things like the relays and the FETs, which are the devices that basically control the voltage of the system, sometimes we'll measure temperature at a distance. So we'll use a product such as a non-dispersive infrared type device or infrared device that will monitor the surface temperature, but it won't be in direct contact with the device. So if for those of you who've gone to the doctor's office, a doctor will use a product that's an infrared device when they take your temperature at your forehead or at a distance. They'll use that little gun and they'll point it at you. That particular technology basically uses a specific zone of infrared radiation that it's detecting, emitting from surfaces that are generating heat. And we do the same thing with our sensor technology. So we can monitor things like high voltage bus work, critical high voltage connections. if you've seen the charge cables for some of these devices, they're fairly big, they're fairly long. They can put a lot of stress on the bolted joints back at the charging station, and those can wear over time. And so you want to be able to monitor those. If those come loose, you want to maintenance that and either tighten those the nuts on that, or potentially even replace it if the wear is too much. And all of those potential issues can generate heat. So we're monitoring heat not only directly with a thermistor technology by making direct contact with these devices, but also being able to do it at a distance. So with our ZTP product line, we're seeing vast implementation of monitoring of FETs for inverter components, high voltage bus work, as well as many of the high voltage connections in the system.
And it warms the little heart of someone like me who's involved in connectors, the fact that, again, we've brought it back a little bit to connectors, in that we do have to remember that these batteries aren't just sitting there alone. They have the need for all sorts of connections between the battery, the motors, the control systems, and it warms my heart that connectors are still involved in that, even when we're talking about batteries.
Yeah, most of our sensors do have connectors attached to them, so we make a pretty big use of that. Now, certainly not the size of the high voltage connections that you might see on a battery pack, but certainly we do wire most of our sensors in the application spaces.
No, it's good to know, but that's not why we're here talking about this today. So, no. You mentioned medical applications, that the fact that the same sensors can be used in a whole range of different things, from personal medical systems to these battery systems. That's really interesting. By the same token, let's talk a little bit about the batteries themselves, because one of the things I've heard recently is about the reuse of batteries that have been used previously for something like automotive. And I think when we were talking beforehand, we were talking about the second use or the second life of batteries. Just as an aside, can you give us a couple of minutes on how batteries are being recycled or reused in the future? Because that's obviously important to our sustainability message.
Yes. The industry is still very much in the experimentation mode. We do have a limited amount of some of the raw materials on the planet: cobalt, nickel, even copper. But you have a variety of different special materials that are used to make these battery cells. So we don't want to landfill them. We want to basically encourage recycling of the material, because in many cases that material is only found in certain places in the globe, which in many cases are challenging to extract from, and even more challenging to move across international borders. But what we try and do is we try and bring the material right back into the supply chain. Now, there are a variety of different approaches being used for that right now. So we have a number of OEMs that are trying to make their battery packs in the application last as long as possible by being able to provide them as a serviceable component. So they may have a large battery pack, but they may be able to service that and provide a replacement module. So the pack may have 10 modules. You may have a module that's starting to let's just say age more than the rest of the system, and you want to replace just that module. There's the capability of doing that in certain applications. Other applications are going kind of the other way, where they're going what they call cell to pack or cell to vehicle, where the cells are basically embedded in a non-serviceable device that forms not only the battery pack itself, but may even form the subfloor of the vehicle, structural components of the vehicle body and chassis. And all of that, even the seat bases may be part of the cover of the battery pack. So that all ends up coming out as one unit. So it does pose some interesting challenges on reuse, but generally on the idea of a second life, is most automotive applications are really going to use only about the top 20% of the life of the battery pack. So they'll want that from, and there's basically two terms I'm going to throw out. The first is state of charge, and that is the amount of charge a particular cell or pack can accept. That's basically the maximum number of electrons you ever want to put in that container. And then you have something called state of health, which is the maximum amount of electrons over time. So very much like we were much more fit, much more capable as we're younger, and as we're aging, we don't necessarily have those same capabilities. Battery pack's kind of like that. As it gets older, it kind of accepts less and less electrons. So and you don't want to exercise it quite as hard. Things don't go as well. So in a typical transportation application, you're really only going to use that state of health from 100% when it's brand new to about 80%. but pack still has a lot of life left in it. And there are many companies out there and developers that are trying to take that pack and take it into another application. And where it's well suited is things like stationary storage. So we've got a number of companies that are partnering with automotive OEMs to accept those packs and then use them in a stationary storage application where they can actually be used in the grid to temporarily store energy and then redeploy that energy. So that energy might be pulled in from a solar array or a wind farm, or maybe just buffering transformers and the infrastructure in such a way that it's shaving peak demand locally. So in those applications, it's well suited. But ultimately, you have that first use, the potential for a second use, and then the recycling process. And the recycling process, the objective is to achieve 90% to 99% of the raw materials, especially those precious metals, back in that supply chain. The philosophies are differing right now. Some OEMs, they'd like to see the battery pack used for the car and then immediately recycled back into making a new battery pack for a car. Now, that philosophy is interesting, and because it basically is assuming that they're going to be able to improve the designs, improve the processing to continue to increase energy density to make the raw materials and the recycled materials more valuable, because now basically they're getting much more efficient in a very short time frame. And then there are kind of a contrary philosophy, which says, I want to make a battery and make it last as long as I can and as many lives as I can, and then take that material back. Generally, these batteries are going to last well in excess of 10 years. We're seeing some claims now from some battery manufacturers of million-mile batteries, 20-year battery lives. So they're actually going to outlast the mechanical components that we use in our internal combustion engines. It's going to be very interesting to see how that market evolves over time, which of these two approaches is going to dominate. But either way, the industry's making best use of its approach to reuse materials so that we're not continuing to extract these raw materials out of the ground.
I think that falls in very nicely with some of the things that we have talked about recently on Design Spark, both in terms of, I won't necessarily call them smart materials, but certainly in recent interviews, we've been talking about the idea of using materials to their most efficient possibility, to the best possible outcome. We've been talking about engineering plastics, for example, that are self-lubricating, that can be reused, recycled into certain applications. And here we are talking about lithium-ion batteries, which, as you say, the things like lithium and cobalt, these are materials with a relatively small reserve globally. We need to be careful how we use that. And so to be able to talk about ensuring that these materials have the longest possible life before they end up, heaven forbid, in landfill, is really interesting. And in fact, I've been speaking in the past with one of my Design Spark colleagues about the idea of the million-mile car, the fact that internal combustion engines, with all their moving parts, all the things that can wear out, these vehicles can't necessarily last that long. When we're looking at electric vehicles, the number of moving parts within them are so much lower. We're talking about electric motors that might even be frictionless contact motors, frictionless motors. And we're talking about batteries where, although we've just learnt that there are mechanical changes that happen within the batteries, that they're not moving parts that will constantly wear out. So I think it's really interesting that we're looking at battery technology and how that's going to impact. And the fact is that sensors, Amphenol sensors in this case, are playing an important role in ensuring that these batteries achieve their full potential, that remain safe for the life that they are used, and then if they go into a second life, that sensors are deployed again to ensure that they can continue to be used. We talked about the idea of a car maybe catching fire by the side of the road. If we're talking about a battery that's sitting in your garage, you can't walk away from it. It's part of your car. It's part of your house. You need to make sure that it's safe, and so sensors are of key importance in that. I think this is probably the perfect time to wrap up this conversation. Brian, I am so grateful that you've been able to come and share not just the sensor information with us, but all this information about batteries, because they are of such importance to the future of our sustainable energy economy. We've been talking recently about the all-electric society where hydrogen is being produced, turned into electricity, is stored, and then maybe turned back into hydrogen should be necessary. There's all sorts of applications, and batteries are going to be super important. So, Brian, thank you so much for sharing all this information with us.
Stay safe, everyone.